into some exoplanets. And now she is one of the co-leads of this cuisines project that I'm sure you'll be hearing a lot about today, which I think is a great model for model intercomparisons. So it's a really fascinating project that you'll get to hear a lot more about. And then I just found out today that she has now been named one of the co-leads of NASA's Nexus. I don't know, is it a consortium, an institution?
Research Coordination Network.
Research Coordination Network. Yeah, thank you. So anyway, before I'm going to turn it over to her in just a second, but I also want to mention that she is leaving us tomorrow, heading back to New York City. So we'll be taking her out to dinner tonight. So if you are interested in tagging along, please see me after the talk today. And there's still room for a few of you to join if you'd like to do that. So with that, I'm going to turn it over to you, Linda. Please take it away.
All right. Thanks, Rory. Thank you for the invitation to talk a little bit more about cuisines, which is near and dear to my heart these days. This cover slide actually is an illustration from some work related to the first intercomparison project that I'm going to tell you about, which is called TIE, but I don't want to get too far ahead of myself. So I'm a lifelong sci-fi fan. I don't know how many other folks here are, since you're in astrobiology. And of course, there's a long history of thinking about the climate of other worlds in various contexts. So of course, we had people thinking about life on planets and climate planets in our own solar system first. So Death by Rain is actually envisioning Venus as a swamp world, as a short story from 1954. And then we also had this novel in the middle thinking about Venus as an ocean world, which we now know is not really the case. And so once the discoveries about Mars and Venus started to come out in the late 50s and early 60s about what these planets were really like, which was really cold and dry for Mars and a hellhole for Venus, the sci-fi folks backed away from thinking about the solar system and instead moved on to other worlds, but they took the ideas with them. So we've got Dagobah on the bottom here, the swamp for Star Wars fans. Not quite another world, but a future world is Waterworld on the bottom there. And of course, Dune and Tatooine as our arid world examples. But this hasn't been confined to the world of fiction. We, of course, had scientists thinking about this early on as well, and Percival Lowell was one of those early folks who thought a lot about Mars as a potentially habitable place. In fact, he wrote 3 books to that effect, and even included this spectrum for water in the Martian atmosphere in his last volume, where he envisioned Mars as being this cold and somewhat arid place with maybe a small amount of arable land, but definitely potentially suitable for life. Now, a lot of these concepts were developed initially through conceptual models, right? That's what we had to work with. But there were early models thinking about simply calculating the temperature of a planet. We had our radiative equilibrium equation from the 1800s. And there it sort of remained for quite some time because, of course, we didn't have information about anywhere else. And so a lot of modeling efforts remain more or less theoretical. And I was sort of interested to think about how that may have changed over time. So I did a quick and dirty Web of Science search on different kinds of modeling. And I tried to weed out the really future Earth oriented stuff. But we can see first, the 1D climate modeling on the top left has always attracted far more interest in terms of the topics examined and the papers that were written. And those have only grown steadily with time. EBMs, more specifically 2-dimensional models and 2.5D models of intermediate complexity, have never been that abundant in terms of tools used for thinking about planets of either paleo-Earth or other worlds. In fact, most of what we see here dates from some earlier paleo-Earth efforts to understand how Earth evolved through time through key phases that usually had something to do with prospects for resource exploitation. And then on the bottom left, we have 3D climate model. 10 years or so. as a tool that was used to think about but also beginning to examine exoplanets environments in general. And the last thing here is the phrase exoplanet climate modeling specifically. And this really only comes up in more recent years, and particularly starting around 2017 or so. And I think that has a lot to do with how the community's attitudes have evolved over time about the utility of various models. We now have a full hierarchy of models from 1D through 3D, that we should take advantage of all of them, and see what we can do, what we can learn from each other and gain in the process. So the foundation of this cuisines idea that Rory mentioned was really our first model intercomparison, where the idea for doing this work came up in discussion over dinner at a Thai restaurant. And it was at the Habitable Worlds meeting in 2017 in Wyoming. And a group of GCM modelers got together and said, well, we have this interest in the TRAPPIST worlds, and we, our individual modeling groups have these GCMs, but we don't really know how they relate to one another in terms of the work that they produce. And that's long been an issue, especially with GCM studies, because if you don't tell everyone about all the things that you put in and any tinkering that you had to do under the hood to get your simulation to run, it becomes very difficult for other people to reproduce your work and understand perhaps how their own work compares to yours, and if there are differences, where those differences come from. So this group of folks at the Thai restaurant decided that they were going to start with a model intercomparison for the topic. That developed into some work that was ultimately published in the Planetary Science Journal as a special edition. We have 3 intercomparison papers looking at the various cases that were explored for TRAPPIST-1E, and a number of individual papers where people thought that their own particular model results had something noteworthy that they wanted to highlight. So Thai was really our first model of comparison. And we just, people hadn't thought about before. A lot of it had to do with assumptions about parameterizations under the hood, and things that had to be worked out so that the actual project could come to completion. Together to talk about their results and talk about what we should do next. And very specifically, the question came up, how do we move beyond doing just this intercomparison of GCMs for the TRAPPIST planets to something that might be equally useful and applicable for modelers more broadly in the planetary community. And so I was in conversations with Thomas Fauché, who is my co-lead on cuisines. We both had a keen interest in trying to expand the scope. And one of the things that I thought might be useful was to take a look at how the Earth side handled model intercomparisons to see what lessons we might be able to draw from how the Earth side handled things. So the main intercomparison project is the Coupled Model Intercomparison Project, or CMIP for short. You may not have heard much about CMIP, but the results of CMIP are fed into the IPCC's climate change assessment reports. Right. So every 7 years or so, the community gets together and they decide on the scope of simulations to run for the next model intercomparison. And that work becomes the part of the physical basis for understanding what might come in the future. Now, in terms of structure,
Could I have you maybe check to see if this camera is one more time?
oh,
I
sure.
think it just, yeah, maybe select it one more time. Yeah, I have no idea. It's selected. Okay.
I'm sorry.
Maybe undo that. We do start video. Yeah. There you go.
Okay, excellent. Okay, So in terms of structure, CMIP has a very large contingent that contributes to the project. There's over 30 modeling groups around the world using an array of models. Most of them are the cutting edge versions of the GCMs of particular modeling groups, but not all of them. Some of them are one step back. Some of them are models of intermediate complexity that might have something to contribute to some other aspect of the intercomparison. And there is a large scale experimental design that is followed. So we start with a deck that's represented by this circle in the middle here of experiments in common. And then there's a whole array of sort of sub-projects that focus on specific aspects of the climate system. And you can see that in the outer circle here with things like chemistry and aerosols, characterizing forcing, carbon cycle, land use, and so on. Those are special sub-projects of CMIP. And along the way, people are looking for things like systematic biases and the ability to improve predictions, especially on shorter time scales. So there's some general goals that the group has in mind. Now, the specific research questions, oops, why is this not going? These specific research questions are selected by the community. So there is the World Climate Research Program, which basically assembles a committee, and the committee members put in their votes for the topics that they feel are most pressing, most in need of development, most in need of attention from modeling groups for the next intercomparison cycle. And they call these the grand challenges. So for the model intercomparison that was finished a couple of years ago, CMIP 6, some of those included focusing more specifically on melting ice and global consequences, weather and climate extremes, regional changes, and so forth. But the important part is that these are community driven in terms of what focal points are selected. And in terms of the actual design of the experiments, again, we have some core experiments that every participating modeling group does, and they are specifically designed to be relatively simple so that model capabilities should not be a barrier to participating with the core experiments. For the specialized scenarios that often require the more cutting edge models, and then those models engage in those particular sub-projects. And then we also have paleoclimate scenarios that are not necessarily looking at specific processes, but exploring different time slices in Earth history with an eye toward understanding if we can identify either what longer term processes might be driving part of future climate change, or what the response might be to a certain kind of change in the future. And for these paleoclimate intercomparisons, they often consist of one core experiment, which is officially part of CMIP, and then an array of other experiments that are less formally part of the model intercomparison project and are decided on by the communities that study those paleoclimate intervals themselves. And in a way, the paleoclimate MIPS are probably the closest analog to what we might have in the exoplanet community. So that was something that I have some personal experience with. Since 2009, I've been part of the Pliocene Model Intercomparison Project, PLIAMIT. And we have specific questions that we ask, but we are open to a broader array of models. And we have alternate scenarios designed to allow different groups to engage at whatever level that they are capable of. Now, in the exoplanet community, we don't necessarily have formal grand challenges defined by the community, but we do have input through the decadal survey, through AstroMap. We had the previous NASA astrobiology survey that highlights the things that the community feel are important. And I've drawn out some of the things here that are potentially addressable by climate models of one sort or another. And so we have a role that we can play, and we can look at these priorities and try to understand what it is that we can do specifically to try to advance the science goals of the community. So we actually have a framework that we can work within. Now we had to think about considerations for exoMIPs. This was the largest problem for GCMs because they take such a long time to run and to analyze, but we wanted to be even-handed across the board, Tama and I, in thinking about what kinds of approaches we would like every modeling intercomparison group to address. So the first is to know what research question you're asking and how it's going to advance the state of the art, either in modeling or advance the state of the science. So it shouldn't be just, oh, let's do Venus because we can, right? There needs to be a guiding concept that focuses the work of the MIP. That experimental design has to have, just as with CMIP, core experiments that everyone can do. And if there are additional experiments that require other specialties, then those can be done by the groups that are capable. But we don't block anyone from engaging in the heart of the MIP. In terms of logistics, there needs to be a plan. So someone has to take the helm and decide, what are we going to do in terms of milestones? How quickly are we going to try to proceed? And what's realistic, given the fact that everyone has a lot to do, right? And there's not a lot of extra funding to get engaged in something like this. And so we recognize that for exoplanets, we are inviting people to participate in their free time. So we want to be flexible, but we also want to be able to see that the MIPS are proceeding forward. Data sharing is really important. This is one area where I think the Earth side falls short. There is a huge apparatus for archiving and distributing data on the Earth side, but it is really difficult to understand. If you don't know what you're looking for, you're not going to be able to find it. And we wanted to avoid that particular problem by making it very clear what diagnostics would be available for analysis, make it easy for people to find what they wanted and download it to use it for other things. And lastly, any exomip needed to have some outcome for observation. So we want to have all the participating model groups take their simulations and generate synthetic spectra, because we want to understand to what extent any difference in model results produces differences in spectra that might influence how we interpret any of the observations that come in from JWST or eventually from Habitable Worlds Observatory or any future mission that is ongoing. So those were 5 organizing principles for pulling cuisines together. Something special about exoMIPs. On the Earth side, there's a lot of emphasis on which models do something right and which do something wrong. We're not there. We're not even close. We don't know whose model is correct and who's not, so we're not trying to identify that. We're not going to say that yours is better than someone else's over here. The purpose of getting these standardized experiments done by all the modeling groups is so that you can understand or begin to understand where models do things differently. You may identify an error that occasionally happens, but for the most part, we just want to understand the uncertainty that is introduced by the different performance of the varying models. They might all be right, they might all be wrong. We'll know better once we have more data to compare against. And I know from speaking to Vicky that she feels that there is a body of knowledge that is ripe to be used for this purpose. And so maybe that will be another project that we try to get underway. Okay. And again, how do we best leverage this array of models that we have from 1D through 3D? Low barrier to entry is really important. But then we also want to be able to think about ultimately how some of these model intercomparison projects might help inform one another with the results that they achieve. So all this thinking ultimately was put into a proposal to the Goddard Space Flight Center SEEK ISFM. So SEEK stands for Sellers Exoplanet Environments Collaboration. ISFM is Internal Science Funding Model. So basically we were asking for some money from in-house. And they supported us in founding Cuisines. This is the first of acronyms for really tortured expressions. I'm sorry, this seems to be a NASA tradition. So cuisines is climates using interactive suites of intercomparisons nested for exoplanet studies. And yes, we reached for that one. But the name cuisines ultimately was inspired by Thai, from the Thai restaurant. And so everything that is part of cuisines is also going to have a food theme. Right. So our motivation really here was in thinking about ways to prepare for understanding observations that may come from JWST or other missions. And cuisines is really a framework. We're not telling people that they have to do something, but we're really strongly encouraging that they do it in a particular way so that it would benefit the largest number of people possible. And so those considerations I enumerated earlier have become the 5 pillars for the cuisines framework. So we want to know what the question is. We want to have an experimental design that works for everybody. We have a schedule that works for as many people as possible, data management plan that shares as broadly as possible and makes it easy to access and utilize data and bring the model output back to observations. We're not passing judgment on whose model is better. As I said, we really don't know. What we do want to know is what are the range of possible outcomes for a given experiment. And it's a work that benefits from the participation of the community, because without the community, none of this happens, right? We really need to have people who are interested and on board. So where are we? At the moment, we have, it's 9 now. Yes, 9 intercomparisons, either underway or about to get underway. That's all the circles here in the middle. I'll go over those in a second. Plus 1 in the corner here called Basel, which is really going to be a collection ultimately of baseline case studies, perhaps for specific targets that we can use to help benchmark later efforts at modeling and future generations of models. So we have models of all kinds for radiative transfer in 1D. We have Malbec, which is our radiative transfer project. So modeling atmospheric lines by the exoplanet community. I told you these are going to be torturous. We have PI, which is 1D, photochemical model intercomparisons for exoplanets. Our newest one is COD ACRA. This is, by way of explanation, this is apparently a Portuguese specialty, sort of like fish fritters. So this is comparing one-dimensional climates of convective radiative atmospheres. We start to move toward higher dimensions. So we have fillet, functionality of ice line, latitudinal, EBM, tenacity. That's a tough one. We have samosa. So this one is a particularly interesting one to me because samosa is actually starting from a whole series of outcomes generated with a model of intermediate complexity called PLASM. And the PLASM folks invited the broader community to look at their results and then try to understand with GCMs when it was okay to just stick with the model of intermediate complexity and the answer that you got would be fine, or when you actually really needed to move on to a GCM, which is important to know because GCMs are, quite frankly, a big time and resource sink. And so Samosa has been working on addressing that. And then we've got some 3D models going. So we have Camembert, comparing atmospheric models of extrasolar mini Neptunes, building and envisioning retrievals and transits. We have CREM, which is about to get underway in mid-November, which is going to be a comparison of reference exoplanet models of Earth. And we have MOCA, which addresses hot Jupiters, basically. And so all of these projects have their specific focus, but from the start, we have been talking about how what we learn from a given project might be able to support the advancement of models in other projects. So, oops. So we have just had our 3rd annual buffet workshop. Yes, another one, building unified framework for exoplanet treatments, where the individual exomip leaders or chefs got to present either their progress to date or their ideas for the intercomparison that they wanted to do going forward. And we always close the workshop with breakout sessions between MIPS, so they can talk to each other about what outputs are going to be generated by this MIP, to what extent can we take that information and put it into another model. Is there a way that we can design experiments where models across the hierarchy can actually do the same kind of experiment to see what we ultimately generate in terms of synthetic spectra? So that is kind of a requirement. You can't just go off and do your own thing. You have to be able to and be willing to engage with other members of the MIP. So where is Cuisines? So we started in 2017. We really started to take off in late 2020. And we have been slowly adding MIPS since then. We are conscious of trying to not have too many MIPS going on simultaneously. It's a small community. We don't want to burn people out by trying to get them involved in too many things all at once. But there is a real role here for graduate students and postdocs who might be interested in getting their fingers into a community effort. It is a great opportunity to meet other people and learn about the models that they're using and some of the techniques that they're using for analysis and so forth. And so we're really looking at all of these MIPS as something that transcends the original crew that started them, that has new people coming on board every time we have an opportunity and a reason to have a new version of the protocol and a new set of experiments to design, as well as new concepts. The potential is very broad. And again, we want this to be community driven. So we ended our workshop last week with a brief poll of some of the topics that were of most interest to people at the meeting. We will be sending out another email to the Cuisines list as a whole to get their input as well, as a way of trying to select what we should add next to our family of MIPS. And so if the idea of Cuisines interests you, I encourage you to come visit the website. You can take a longer look at the description of the individual projects. Those projects that have data available already, those are linked because we have a special repository for Cuisines related experiments called CCAM. And some of the early papers that have already been published for the protocols are also available on that site. And there is on the first page a link where you can sign up for emails to be on the Cuisines mailing list if you want to keep abreast of all the developments that we have coming. And so I just want to acknowledge, first of all, the Cuisines Working Group and all the people who are the chefs of our MIPS. We would not be anywhere without them again, and all of the people who are participating. It's really amazing to me to see how the individual MIPS grow each year with new people engaged. And I just wanted to give special thanks to Sean Domagold-Goldman, who really was a staunch supporter for Thomas and I from the start in getting the Cuisines concept funded, the Nexus for Exoplanet System Science for having us as a working group and helping to promote us with headquarters and make us look good. And also Seek for providing a little bit of funding to Thomas and I so that we can keep the ball rolling and keep all of this coming to you folks. And with that, I'll end and take any questions.
Thank you, Linda. So we have time for questions.
Great, really interesting, and I'm watering at the mouth. That was good. So I'm wondering if you could highlight some of the results that have come out of the, say, Thai or earlier cuisine efforts that have really advanced the field of setting either Trappist one, either system, or other.
So with I think with Thai, really we were able to highlight where there were some key differences. So in one respect, it turned out that the Rocky 3D model was in a different rotational regime than the others. And so we were off in one direction and Other folks are over here, and we still don't know quite why. But that is a point of interest that we are keeping in mind as we move forward with additional experiments. For some of the MIPS that are a little further along, I think one of the, sounds strange, but one of the initial findings was that they had to be really careful about designing the experimental protocol, because if you were not very specific, the initial results would be kind of all over the place. And then it was like, oh, we forgot to stipulate, you know, and so that's just part of the growing pains. But for Malbec, I think one of the things that they found that really startled them was that the atmospheric layering made a huge difference in the response that they got, and they were not prepared for the spread of responses that they had. Camembert has run into some interesting issues with trying to define the surface of a mini Neptune. How do you actually do that, right? And what will work for everyone? For Somoza, Somoza has thought about ways to do sparse sampling. And they are adapting a methodology that was originally designed for mining engineers as a way of filling in some of the spaces. And they're finding it works quite well. And they're looking at trying to expand the scope of that technique to other model types beyond the ones that they've been using so far. There will be, probably by the end of this week, a link on the Cuisine's website to the videos from last week's presentations. So you can see what the MIP leaders have to say about the progress that they have made individually. And a lot of that is work that is in the process of being written up as we speak. We also discovered as a group, actually, that having papers that centered on protocols was something that reviewers did not quite get. I can say for the Cuisine's framework paper as a whole, one comment I got was, but there's no science in here. Because they were expecting actual experiments to be done without recognizing that you need to tell people how to do the experiments first, right? So that's something that we are also trying to address at this point so that we can get the word out. And you can consider that perhaps a bit of a teaser, right? You know, oh, look, here are the early results, you know. But come join us, right? It's never too late to come join a MIP.
Any other questions here?
Cool. I was curious if you could say a bit more about the new one, like automated convective model comparison. Like what are the main science behind that?
That is brand new. That was actually Thomas' recruit. And so honestly, I can't repeat the details. The 1D model is not my area of expertise, but Guillaume has a presentation which will be available, and you can see what Guillaume is thinking about in terms of his MIP. But because it is literally just getting started, he is going to be open for comment and suggestions. So the experimental design for that has not yet been set.
Are there any online questions?
Not yet.
Not yet.
I asked.
Okay.
Probably not.
All right. Well, if there are no more questions, let's thank Linda again. And if you would like to come out to dinner, please come down and let me know.